Hello, everybody. Welcome to today's webinar. We are so excited to get started with you all. Before we dive in, I'd love to have you navigate to the bottom of your Zoom window. On the bottom of your Zoom window there is going to be something like a little chat box. If you click that chat box, you'll be able to select sending a message to everyone. Make sure that's selected and go ahead and type in that chat box what the last movie you saw in movie theaters was. So again, make sure your chat is set to everyone. And the reason I ask that is because Fran and myself will be answering questions during today's webinar. We like to look like we're not talking to ourselves. So we ask that you send your chats to everyone so that people can kind of follow along and say, hey, that was my question. And it looks like we've got a few movies rolling in already. Deadpool 2, I've heard great things about that. Let's see, Star Wars, holy cannoli, Randy, that's awesome. It's been a second. That's a good last one to have wrapped up on. Another Deadpool 2, very nice. Hands of Stone. I'm trying to think, mine honestly might have been Barbie last summer. So I can't think of another one I've seen, but that was a fun time. Let's see. And for those of you who just arrived, we're just getting to know each other in the chat right now. If you want to navigate to the bottom of the chat and let us know what the last movie you saw in theaters was. Oh, good. Someone else, the last movie they saw was Barbie. I knew that I wasn't alone in that one. Amazing. All right, well, I think some folks are still getting settled in, but to make the most of our time today, we'll go on ahead and move forward. Before I pass you off to our fantastic presenters, I did just want to let you know a few housekeeping items first. First and foremost, you will receive a recording of today's webinar. It usually takes us about 3 to 5 business days to get it edited and then uploaded onto YouTube and our website. But as soon as it's up and live, we're going to go ahead and email you a link. So keep an eye on your inbox and you'll see it there. That email will also include a link to a resources folder. I'm going to drop a link into the chat to that resources folder as soon as I'm done talking. And that'll just have things like your certificate of attendance, amazing resources we've pulled together, and more. So make sure you check that out. The other thing I wanted to mention is that we do want to answer your questions today, so please make sure to use that chat box. Let us know if you have any questions. If we happen to not get to your question today, please reach out to us via email, chat, call, whatever works for you. If you want to email us, you can reach us at physics@vernier.com. With all that being said, I will pass you off to today's presenters, and thank you again for joining us.
Hello, everyone. I'm John Gastineau. I've been at Vernier approximately forever. Well, that's not quite true, but 25 years. And I've always done video analysis. It's just always been a lot of fun and been a part of my physics teaching for a very long time. But we also have Fran Poudry. Fran?
Hello. Oh, am I supposed to say something about
Oh,
myself?
yeah, give us 2 sentences.
I'm the director of physics here at Vernier, which I've been here at Vernier for 11 years now. And before that, I have over 20 years experience in high school teaching physics.
Great. Thank you very much, Fran. So Fran is going to be paying attention to the chat so that I don't have to, and will be relaying questions to me. So I'm going to be doing most of the talking, but I do want to make this as interactive as we can. And so I want to try to respond to as many of your questions as I can as they come up during this informal presentation. This is, let's see, let me start to share. This is intended to be a pretty basic introduction to using the app Vernier Video Analysis. So if you've already been using it, you're going to experience the pleasure of being told things you already know. But I hope you will find some nuggets in here and things that will help, that everyone will find some nuggets in here that will help you to make good use of this with your students. And I'm going to start by doing some basic analysis and calling out some basic features of the application. And then we'll jump into some more advanced things. And I will refer to some exercises and that are in our some books. And uh, there will be a link in the resource folder. We'll have some handouts, and one of the things that'll be in there is just my notes that I wrote up to speak from today. That's just a thing I used to do when I was in the classroom. As rough as my notes were, they're better than handing out nothing. But yet they can be very current about what I've just decided to do. So in that spirit, I've made available the notes that I'm going to work from. So yeah, video analysis. So I'm going to show my age here. This is the physics book I used in high school, the PSSC physics, and way back then, the book had a strobe image right there on the cover. Many of you have seen these where it's a still photo, but where the shutter is open for a long time, and there's a strobe light going, capturing the position of an object as a function of time for a short period of time. And here's a strobe image of a bouncing ball. And this kind of strobe image is something that physics teachers used way back in the 50s and 60s when PSSC was big to help students analyze two-dimensional motion. Now, with a strobe photo, the time base is the clock, as it were, is the rate of flashing of the strobe. Every time the strobe flashes, you get another image on the screen. With video analysis, we're going to do that differently. We're going to use videos of an object in motion, and our clock is going to be each successive frame of a video. So without going into a lot of detail on the application just yet, I'm just going to get a video in here, and I'm going to make the video big so that everybody can see things in here. And I have a basketball shot. As a physics teacher, okay, parabolic motion. This is absolutely core stuff. We could go to town with this in an intro physics course. But in this video, remember, a video is just a bunch of still photos. So this is equivalent, as I'm just clicking to advance frame by frame, and you can see that this is analogous to that strobe photo. I'm going to rewind, as it were. It's funny we still use that word, and begin tracking the position of this ball. And I'm just going to move my fancy cursor on top of the basketball and click. And you'll see that I'm getting a trail left behind. Every time I click, the application records the position of the basketball and advances the video by one frame. And then I am moving my cursor to the new position of the basketball, and sometimes marking more and less carefully, but we'll get there. And as I go, I'm able to trace out that nice parabolic path of the basketball. And that's as far as I'll go for the moment. Let's take a look at the actual data that I've been collecting. And I'm just rearranging my screen here so that we can look. Let's first look at a data table. My first column is clock time. That's my clock. The steady beat of the frames shown in the video. Then I've got a couple of columns of X and Y position of this object. I haven't talked about an origin yet. I haven't talked about a scale yet. that's all yet to come. But as you see on the video, I've tracked the X and Y location of that ball. And in fact, I can draw a graph of the X and Y location of that ball. The red dots are the horizontal position of the ball as a function of time, and the blue dots are the vertical position of that ball as a function of time. Or I could even do something like this. I could say, let me have the vertical position as a function of the X position, the trajectory of the ball. So a number of ways of slicing and dicing this, the data. But you see how this matches the idea of that strobe photo. I'm just tracking an object as time moves on and extracting that position information. Now, let's look at a few more details here. I'm going to go back to my video, and I'm going to now set this into some physical units. Because if you look in my data table, the X position is just in pixels, because the application has no idea how what the scale of this video is. But happily, somebody left a meter stick on the ground, and that meter stick happens to be in the plane of the motion. I'm going to show you another image later on about how important that is. But a good video for video analysis typically is a pretty boring video cinematically, because the camera doesn't move, it doesn't zoom, it's just kind of looking square on at the motion. And it includes an object of known size in the plane of the motion. So I'm going to tell the software I'm going to set the coordinate system, and it drops this dumbbell in here, and I can drag it around. It's kind of like a rubber band, and drop it on either end of my meter stick. And there's a field up here, which is giving me my conversion. The application tells me, okay, that's 240 pixels in the video. I can tell by looking at it that that's a meter stick. I kind of wish it had been a 2-meter stick, but I'll have to have an argument with past self about my choices back then. But it's a meter stick, and so I can enter a 1 and the units of meters. And take a look though at the data table of after having done that. I've given the software the conversion between pixels and meters. And so now my data table can be X and Y position of the ball in terms of meters. And my graph updates as well. Now, what about the origin? Well, we don't have to set that. There's a lot of good physics we can do with that trajectory and with the parabolic function there that we get with the Y position as a function of time. But let's at least understand where the origin is. Again, using the system tool, I can say, let me set the origin. And you can see I just have a standard Cartesian coordinate system, and I could drop that wherever I want. And if I do that, here, let me do that. So you keep eyes on the data table. And if I drag that somewhere else, you'll see the numbers change in the data table, but the qualitative shape of the graph doesn't change because the location of the origin doesn't affect the physics there. In this particular problem, I don't really care where the origin is, so I'm just going to leave it down there. And let's look a little more closely at the data now. I haven't talked yet about these other columns. From the X and Y positions, the software can calculate velocities in X and Y. And that is simply a numerical derivative. Again, I'm going to talk more about the details of that later. But that means that I have a number of options here. I've got this nice graph of Y as a function of time, but I could also say, let me have Y velocity as a function of time. And in fact, I get, to all of us physics teachers, You're saying, well, of course, we've got a linearly, a uniformly varying y velocity as a function of time. And I'll bet you the slope of that line has a very nice value. And let me do a linear fit. And okay, I wasn't super careful, but I've got a rough estimate of little g with the slope of this fitted line. And we can talk in a bit about why that might not be a better value. Um, but I can also do other things. Let me go back to that y position as a function of time. And I could come in here and do a quadratic curve fit. And I've got another way of extracting the vertical acceleration of that basketball. So this is just super basic video analysis. The concepts here are I've got a kind of a boring video that where the camera is not moving, but the object is moving, and I'm tracking that object as a function of time. And I've got a scale object in the video, and between those things and following that object frame by frame, I can extract motion information. Now, this is a powerful thing in the classroom because uh, collecting a video is pretty straightforward. And so students can collect these themselves and use them to analyze a wide variety of uh, of, uh, of situations. Let me pause just for a moment. Fran, have we had any key questions come in? You're muted.
There we are. Sorry, I'm using a double monitor here, and I was having trouble getting my cursor to the correct screen. We have not had any questions yet.
All right.
So if anyone does have any questions, feel free to pop them right in the chat.
Yeah, please do. Okay, now let me go into a little bit more of the nitty gritty of this application. I am using Vernier Video Analysis. It is a web application, and that means that while it's a regular application, it also lives in a browser, which makes for a little bit of weirdness. Um, and that weirdness primarily has to do with how it saves files. Um, but I've got a file menu up here, and I can choose to save this. And let's see. Actually, Fran, is this is my save as dialog showing?
Yes, it
Yes,
is.
it is.
Okay, great. Zoom is funny that way of not always showing the folders that you want. So when I choose save as, just like a standard computer application, you're given the opportunity to save this to a location of your choosing. If you have your browser configured uh, to let you choose where to put downloads, because as far as your browser is concerned, this is a download. But you could just save a file as you would with any other application. Um, and you can, of course, go in and if you were to choose a new file, a new experiment, you could choose to open a file as well.
So
A
John,
couple,
we do have a couple of questions coming in now.
sure.
So i- first one is, are you going to talk about capture, video capture?
Yes, yes, we'll get to capture. I'm going to move along pretty quickly here to some concepts like that.
All right. And then there was a question about how well does this work with Chromebooks?
Great. So the video analysis application, being a web app or progressive web app, to use the words the developers use, this runs in a browser. That means that you can run this on a Mac, as I am doing right now. You can run this on a Windows machine. You can run this on a Chromebook. You can run this on an iPad or an iPhone, and you can run this on an Android device. In every case, you're just running this within a browser. And because it's the same app, the tools the analysis of, abilities, really everything is exactly the same regardless of the platform on which you are running the thing. It's certainly a little bit easier to interact with the video on a computer than it is on a phone, just because of real estate. But it is the same application.
So related, is there a browser that is more preferred?
This will work in Safari and in Chrome and in Edge. It will run in other browsers as well, but we don't test there, so I'm not going to make any promises about those other browsers. Uh, but since Chrome is what's on a Chromebook, and Safari and Edge are what come natively on Macs and PCs, you're pretty much good to go, regardless of the platform you're using.
And then uh, another question, and this will be the final one from this batch, but maybe you're going to speak to it, is what's the best way for students to get videos into video analysis?
Ah, yes. When I talk about capture, we'll talk about a couple of different workflows to do that. I just want to point out one quick thing, because you might notice that I didn't mark my points with great care. Let me back up a few frames and you can see that, um, well, let's see. Yeah, there I kind of didn't quite get the middle of the ball. I'm being picky here, but I need something so I can talk about editing. I've clicked this edit tab, and my cursor actually turns into a little grabby hand, and I can drag a point around and adjust things so I can do a little bit better, if I didn't click well in the first place. And while I'm clicking that, notice there's a trash can over there. And so if I just decide, no, I don't want that point at all, I can drag it over to the trash can and uh, get rid of it. A couple of other things to take note of. There's a gear down here. Um, this will allow you to do things like skip every other frame or every fifth frame. If you took a video at too high a frame rate, that's nice to have. And also,
John,
yes,
so another question came in, can arrow keys be used for higher precision?
they can. It depends a little bit on your browser settings. The One of my tips for high precision of marking videos is just to make your video as big as possible. And one of the things you can do is turn off your graph, turn off your data table, and just make that video big. And just that way, you place as low a, a, a priority on your mousing ability as possible. And that, for me, that's been the best way uh, to really do that carefully. And let me say one more thing, a couple more things about this app. Um, your questions got ahead of me. Uh, as I said, Safari, Chrome, and Edge. And one of the fun things about this, you access it just by a URL, so it's very easy to distribute to your students. You just give them a URL, and they'll get right in. Oh, and speaking of that, as part of this webinar, in the package you're going to get, um, you will get a link to a form to generate an immediate 60-day access code for the Vernier Video Analysis. So if you make sure you take advantage of that, because you'll have a couple of months then to play with this, and you're welcome to share that URL with your students. Um, and when you do obtain this app, subscribe to this app, it is a site license, so it's very easy to share with all of your students, and even if they're running it uh, on their personal devices. Um, Video analysis is part of the analysis suite that includes graphical analysis pro, spectral analysis, and instrumental analysis. A couple of you asked a question in registration of why is this not part of graphical analysis? Well, it's not part of graphical for the same reasons that spectral and instrumental are not part of graphical. There's a slightly different workflow for doing video analysis and for using a spectrometer, for using a polarimeter, things like that. And so we decided to split these off into independent applications. But even though these are separate applications, they share the same DNA, and they have the same analysis tools. If you compare, you'll find that video analysis has exactly the same analysis tools as Graphical Analysis Pro. Let's see. Some other things that VVA does goes beyond this essential video analysis that I've already shown you is vectors, the use of polar coordinates, center of mass calculations, and distance measurements. I'm going to quick show you vectors just because it's kind of a fun thing. Let me. Now I'm going to wish I'd done a more careful job of marking my points and marked more of them. But I am going to come over here. Oh, I'm sorry. And go to the add area and ask to see vectors. This allows me to superimpose vectors for position, velocity, and acceleration on top of my video. And I'm going to enable velocity vectors. And right now it's showing both vertical and horizontal components as well as the total vector. I'm going to set it so it's only showing the components for simplicity. I'm going to set it so that I'm only showing a vector every other point, just to not clutter the screen quite so much. I can control, as you can see here, I can control how often those points fill in. And I can also set the size of those vectors, so I can choose a scale for those vectors to make them as visible as possible. And this is just a scale factor because if you stop and think about it, there's a units mismatch here. We've got the vectors in units of meters per second, but I'm drawing them on a video field with units of meters. So of necessity, I have to have a scale factor. But let's take a look at these vectors. And even though my marking wasn't all that careful, you can see that the horizontal velocity is staying fairly constant, and the vertical velocity is large at the beginning and getting smaller in magnitude, but still pointing up, and then it changes sign. You know all this, but the vector display is just being drawn based on the numerical values in that data table. So don't miss this vector display feature. You can also use the acceleration vector, but I got to warn you, um, because the acceleration is the second derivative calculation, it depends on careful marking of your of the object position. So you need to do that marking with a certain amount of care. Finally, let me before I jump on to capture things, let me mention. Let's see. Let me mention auto tracking because it may help with that accurate marking. I'm going to start a fresh version of this experiment. And just basically I'm throwing away the points I've already made. I'm going to back this up, and I'm going to bring in this new cursor, and I'm going to center it on the basketball and set it so that the active area is about the same size as the basketball. And I'm going to say auto track. And it does exactly what it sounds like. Now, I'm a word to the wise. auto tracking is a great tool, speeds things up and it takes care of the tedious part, but you do need to do this with carefully prepared videos. Notice on this video, the background is very plain. There's no competing pattern. There's nothing else that's going to confuse the tracking engine. And there's a lot of contrast between the basketball and that gray background. So this is an ideal background for using auto tracking. If you have a video that is just collected in a classroom with a typically complicated background, you're going to find that the tracking will uh, will be challenged to track an object for very long because of that cluttered background. So if you want to use auto tracking, you do need to prepare uh, the video with a little bit more care.
John, we've had a question about the number of points used in uh, derivatives and if that can be changed manually.
Yes. Just looking at the clock, I think I'm not going to get to my collision video, so I will talk about derivatives here. I mentioned that the velocity columns are calculated using a numerical derivative. That does not do successive differences. In other words, it's not just delta x over delta t. Delta x over delta t just takes differences between numbers of small differences between large numbers, basically. And that's a recipe for a noisy derivative. Instead, we use 3, 5, or 7 points and effectively fit a line to those points to find the velocity. But you can go into the session preferences and alter the number of points used for derivative calculations. If you have a motion that is where you don't have a lot of points, but you want to get a responsive velocity value, you can set this back to a smaller number. And if I do it here, we're barely going to see a change. Oh, let's see. Let me display a velocity graph so you can see a change. If I change this number here, you can see in my graph in the background that the graph becomes quieter if I use a large number of points, and it becomes a little noisier as I use a small number of points. So you can customize this derivative calculation to the video at hand. Like life, this is compromise. You got to make a compromise between the how much noise reduction you've got by using a lot of points to calculate the velocity, or responsiveness to changes. And if you're doing something like simple harmonic motion, you may need to use a smaller number of points. Let me quick mention, we do have some curriculum available for these. Um, there are 2 books, Motion and Sports and Conservation Laws and Forces. And Fran is actually the principal author of these books. She did an awesome job with these. And these were done in concert with a human physiology guy here on staff, John Melville. And so many of these examples have to do with analyzing sports. We've got some samples in the webinar folder. One is a cart collision experiment, and another is Coulomb's law, which is pretty interesting. It's also a hard one because you have to mark your points with great care. Let's see. There was a question already about capture tips. Let's talk about some of these. And in your packet, there is going to be a link to a blog post that Fran wrote for us that includes these points and others. But here's my short summary. Uh, you may have gotten a video of, say, a falling object, an object in free fall, and been frustrated because the object is blurry. That's usually because the shutter speed isn't fast enough for the motion. And if you give your camera lots of light, uh, it will adjust by using a fast shutter speed. That's shutter speed as opposed to frame rate. Fast shutter speed, which will freeze the motion better. The image needs to be taken square to the motion so that the object doesn't change distance to the camera. And think back to that basketball toss video that we started with. Uh, the ball is moving in a plane that is perpendicular to the view of the camera, and that means that the ball is not changing distance to the camera very much. Um, and I'll come back to that very much thing in a moment. Um, I mentioned a scale object. In that video we used, there was a meter stick. It would have been better to have a 2-meter stick. We've learned about that, and now include a big honking red 2x4 that's exactly 2 meters long that we include in our newer videos. Uh, Another thing that helps get good videos is to avoid using a wide angle lens. That's tempting to do in the classroom because you don't have a lot of space. Uh, but that means that as an object moves from one side to the other side of the video, that it's actually going to be changing distance to the camera in in a significant way. And so you will reduce parallax errors, by backing the camera off as far as you possibly can, which basically means using a telephoto lens. And that will markedly reduce parallax and improve the quality of your videos. You got to make sure that the object is very visible in the video so that you can track it, or if you've prepared a nice clean background, the auto tracking can track it. And a good idea is to trim that video on the capturing device if it's possible. Just the reality of capturing a video, typically you might keep keep it going for 30 seconds or a minute or 5 minutes until you get just the motion you want. Um, but if you then move that whole long video that's mostly junk over to video analysis, that's just going to be a burden because it's a large video. It's just too much trouble. So if you can trim that on the capturing device, that's the best thing to do. So capturing device. Um, Here's kind of a hierarchy of tools, and you got to choose what works in your classroom. Um, Now, if I'm setting off to do a really good video, I'm going to pull out, my expensive interchangeable lens camera that I do bird photography with, something fancy, but that's expensive, and that's not really practical for the classroom. So, what are the better bets in order of preference? These days, a phone is really your best combination of high quality and ease of use and accessibility. Phones today have telephoto lenses. If you give them lots of light, they will use a fast shutter speed. And the camera apps allow you to trim your videos down, even do things like perspective correction. You can get exactly what you want with that phone. I know some schools are moving to not have student phones available, but if that's the case, you as a teacher are going to have to figure out some other options. One option might be just to find some cheap used phones and make those available, because a phone without a social media login isn't nearly as much fun, at least for doing non-physics things. iPads, tablets, they've got cameras these days that are nearly as good as a phone, and they also offer that really nice video editing to do your clips uh, for, uh, for videos. Uh, Point and shoot cameras, and by this I mean a $200, $300 still camera. Those cameras today have video modes and will take really high quality videos, possibly at higher frame rates. Um, uh, Phones generally do higher frame rates if you need that. But the point and shoot camera is going to dump a video onto an SD card, which you then need to move over to your computer or Chromebook. Uh, as I said, the gold standard is an interchangeable lens camera, which, well, you're probably not going to buy your own, but hey, maybe your school has that available for loans, and so maybe that will be something that you can make use of. Things that you can use in a pinch, but you may be frustrated, especially if you want to do something involving free fall, is using a web camera, or a flip cam, or there are these cheap video logging, blogging cameras that tend not to give very clean images. Um, they're cheap, but it's a you get what you pay for problem. So here's an array of things that you can use. Um, my two go-to things for most of the time, I pull out a phone. And if I'm really wanting to be careful, I will use an interchangeable lens camera. Um, but those are pricey.
We have another question that came
Please.
up. Are the calculations performed in the cloud or on the local computer running video analysis?
Oh, that's a good question because that lets me talk about privacy a little bit. Um, the video analysis web app is an application. It runs entirely locally on your computer. And you can even demonstrate that to yourself by getting the app in a browser tab and turning off your internet connection. And you'll find that this thing runs just fine. It doesn't need the internet once it's gotten itself downloaded into the browser. As a result, all the calculations, like the velocity calculations, are done locally by the browser. The video is not uploaded to the cloud. It kind of feels that way because, hey, you're in a web page and you're used to doing things like uploading videos to a cloud, but nothing like that happens. All of this runs locally on your own machine. And we have no idea uh, what's being done with these applications. Is totally private because everything happens on your own device. Was there another question?
That was it.
Okay. Oh, I have one more image in my slide deck that I just wanted to show because I've been talking about parallax error and using a telephoto lens and having your scale factor object, often a meter stick, in the plane of motion. So I've got 5 meter sticks here. They're all the same length. They're meter sticks, but they're different distances to the camera. And so they're all differing lengths in this image. If I am doing a ball toss or rolling a cart down a ramp, doing something like that, the if the meter stick is not in that same plane of motion, clearly you're going to be introducing a significant systematic error in that video. So having the object in that plane of motion is really crucial. Um, we often get questions, why does my value for little g not correct? Well, uh, 6 times out of 10, not every time, but 6 times out of 10, the problem is that the meter stick was sitting way behind the motion. Also, this image looks the way it does because it was taken with a wide angle lens. Had we used a camera backing off, doubling the distance to the meter sticks, the meter sticks would have changed in the perspective, would have made the meter sticks appear much closer to the same length. So this is why I'm always saying use the telephoto lens on your camera whenever possible, because it will reduce the parallax error, and it will do a lot better. All right, I am going to do one more example, just because I know that this is something that came up in the questions. Oh, I'm changing my mind on the fly. You guys can let me do that. Um, I'm going to start with some candy, or end with some candy. This was from Apollo 16, grainy image and all. So this is pushing 50 years ago. And the astronaut jumped. And we have this astronaut was in free fall for that little bit of time, but G is not 9.8, is it? This is a pretty quick one to mess with because there aren't very many frames. I'm just going to advance to a frame where you can see his boots have left the lunar surface. And I'm just going to track the corner of his backpack. And I don't want auto tracking. Just going to track myself. And I'm going to click. So I'll just do a few of these here and follow the position of the backpack. Oh, here's a hint. Sometimes the trail gets in the way, and so I've just turned off trails so that I can see what's going on a little bit better. And now let's take a look here. And I have let's see, really all I care about here is the Y motion. And you can see, okay, I could have used more care with marking that, but those points are more or less in a parabola. Sounds like uniform acceleration. Now, darn it, they didn't put a meter stick out here. What can we do? Well, this is an example of using a found image, a found video, to do video analysis. Let me just replay this video because realize this is exactly the sort of video that we need to do video analysis, because the camera is on a tripod. Clearly, there are only two astronauts there on the moon. There's not somebody else holding a jiggly camera. So this camera is staying put, which makes for a good high quality video for this purpose. And the motion is in the plane perpendicular to the view, because he's just going up and down in the same spot. And that's pretty good for being able to track this parabolic or this free fall motion of the astronaut. Well, I don't have a meter stick, but I do know that astronauts are, well, they're taller than 1.5 meters, and most of the astronauts were kind of little, honestly. They were often 5'6", 5'8", because they had to fit in those small capsules. So he's probably, he's not 2 meters tall either. So I'm going to just come in here and say, okay, I'm going to take a wild guess and say that my astronaut is 1.8 meters tall. And clearly that's not, I'm making a guess here. Maybe I could do some Googling and figure out what's going on. But um, uh, but this is good enough. And my graph has rescaled with this scale. And now let me do a quick quadratic fit. And I see a quadratic fit parameter of minus 0.8 meters per second squared. And we know that that's 1/2 the acceleration. So twice that is about 1.6 meters per second squared. 1.6, hey, that's about 1/6 of 9.8. And sure enough, the gravitational field on the surface of the moon is about 1/6 that of the Earth. So real quickly here, you can do some nice physics, even extraterrestrial physics. So fun stuff. Uh, Let me remind you all that there is that resource folder. This moon video is in there, as well as a video for doing the Coulomb's law experiment and some colliding cart experiments. I haven't mentioned at all using this object menu. You can track multiple objects like 2 or more carts. You can do center of mass calculations. And one of the exercises that I provide to you in that resource folder has to do with colliding carts. So you can do uh, momentum conservation and energy conservation, and do that with your calculated columns here in the data table. And if you're a graphical analysis user, that'll be very familiar because it uses the same interface that graphical analysis and graphical analysis pro use to do these sorts of calculations. So take a look at these books for other ideas, and you'll find that there's a lot of good physics you can do with Vernier Video Analysis. That's most of what I intended to talk about today. So I'm going to stop here and field questions for the rest of the time.
So we're getting a lot of thank yous in the chat, and I'm not seeing any new questions. There was a question about doing auto tracking and manual if there was a time period when the auto tracker couldn't see the object, and I answered that if the auto tracker loses the object, then it stops tracking and you just manually move the cursor to the object.
It, exactly. The um, that's a good way to think about it. If I just quick do an auto track here, like have already demonstrated, I know it's going to lose it at the bounce. Oh, here's kind of a fun little history bit. We have to decide if the tracking is working correctly because it doesn't know what the objects are. It's just doing pattern recognition on the video. And so the algorithm behind the scenes is on the fly calculating the object acceleration. And if the object acceleration suddenly changes by a lot, we decide that we've lost the object, and the and so the auto tracking stops. In this case, the acceleration changed by a lot because it was a bounce, and so that's why it stopped at this point. Um, and the developer who did this, he actually was a high school student who was doing an internship with us, and he labeled this subroutine the suspicion engine. Because if the acceleration is too large, he suspected that the object had been lost. So you're seeing the suspicion engine in play here. But the object got lost. I'm just going to move my cursor back to the ball and hit auto tracking again, and it picked up where it left off. And so you can use a combination of kind of assisted auto tracking, or if there's a region where the auto tracking is just failing, just auto track as much as you can and fill the rest in by hand if you want.
We did get a question about what video file formats are supported.
Good. We support just about anything now that you can capture with a phone or still camera. One of you in the registration asked about high efficiency videos. So I'm glad this question came in. Before Video Analysis 3.0, and when browsers were a little older, the browsers struggled working with the native format on phones, which was a high efficiency format designed to have small file sizes. But as browsers have gotten better, we've been able to use more features in them. So with the latest release of Video Analysis version 3.0, we have enabled the support of high efficiency videos. So for the most part, any video that you capture on a phone or a camera, you'll be able to just insert uh, into Video Analysis um, using this import video button. And if it doesn't work, you can do a conversion. And we've got information in our TILs about, in our technical library about doing these conversions. If you need some help with that, shoot us an email to physics@vernier.com and we'll be happy to help you with that. Oh, and if you're using a device that has a built-in camera, like a phone or a tablet, if you click import video, one of the options is to use the camera. So you can just do video capture right into the app if your device uh, has an accessible camera in it. So most file formats now work. It's a big change from the previous version of video analysis.
Another question is there a minimum memory for computers using Vernier Video Analysis?
There probably is, but in practice, any computer or Chromebook or phone that is good enough to browse to modern websites is going to work just fine for doing basic video analysis. You might remember that I suggested that you trim your videos before importing them. If you bring in a 5-minute video, you may be challenged by the browser running out of memory. But for your typical short videos, just about any device is going to work, and this includes 5 and 8-year-old computers and Chromebooks. This works just fine on Chromebooks that are no longer getting security updates, for example. It's really not an issue.
And another question, I think the question is actually asking, can you open video analysis files in Graphical Analysis Pro and vice versa?
We don't directly support opening VA files in GA and vice versa. However, you have the same analysis tools in video analysis that you do in graphical analysis. So mostly that isn't necessary. If you did want to move your video analysis data into graphical, you can always copy and paste using the clipboard and paste it into graphical analysis. And that reminds me, in a registration question, somebody asked about synchronizing videos to sensor data, like you could do in Logger Pro. And you can't do that in video analysis because video analysis doesn't do anything with sensors. But Graphical Analysis Pro does allow you to collect sensor data and insert a video and synchronize it to the sensor data. So you can accomplish that same Logger Pro-like behavior in graphical analysis. But because that's a sensor-related feature, that's something that is done in graphical as opposed to video analysis. We're coming up on an hour here, so I think I'm going to stop. Fran, maybe one more question if there is.
Nope, no more
Okay,
questions.
very good. Well, this has been fun. Do take a look at that resource folder. Fran and I are available for questions. The quickest way to get to us is pop us an email at physics@vernier.com. And we love to talk about video analysis. It's a lot of fun.
We just got a great comment that it says, I found new things despite having used the software for 3 years already.
Yeah, it's funny. I tend to go back to basics whenever I explain things to people, even if I know that people have used it a lot, because there's always something there that there is to learn. So I'm glad you learned something.
All right. Well, have a great rest of your week. I hope you have a fabulous Wednesday night. And thank you again for joining us, everyone. Have a great rest of your day.